Hello friends, in the previous sessions we've been looking into a specific problem, and based on the problem we have been trying to understand certain fundamental concepts of statistics. So the problem that we have been considering is we've been working on some alloy developments, and so far we have tested or we have developed close to n different alloys, and we have measured rather the lattice parameters of each of these alloys. So essentially what our data set comprises of is just the lattice parameters of the n different alloys that we have developed. Now we are developing a new alloy, and we want to know what could be the probable lattice parameter that this newly developed alloy can assume. Now what essentially we have done is this data set, that is just a single column data set, and each entity in this column it comprises of, so it's a single column data set, and each entity in this column it comprises of rather the lattice parameters, and there are n data points associated with it. Now this being rather a univariate data, or rather just data with that is just a single variable, just a single independent variable, what we have essentially done is we have rather placed, based on the magnitude assumed by the lattice parameter, we have placed it on a scale, and the range, so the range of the scale is based on the least and the maximum magnitude that is assumed by the lattice parameter. Now supposing we assume that the least value is 0.05 angstrom and the maximum value is 0.6 angstrom. Now supposing if one of the alloy that we have developed assumes a value of 0.06, it will occupy a space or a position on the scale close to the least value, or the least range that we have considered, the least range of the scale that we have considered. Supposing there is another alloy that occupies or that assumes the lattice parameter of 0.5, the position occupied by that alloy on the scale would be here. So depending on the magnitude of the lattice parameter assumed by the alloy, we are placing the corresponding alloy on the scale that ranges from the 0.05 angstrom to 0.06. Now when we keep on placing our alloys based on the lattice parameter on the scale, what we essentially end up with is a population distribution, meaning we will be able to rather visually see that where these alloys occupy a position on this scale here, which rather assumes or which rather quantifies the magnitude of the lattice parameter. Now when the population of the alloys are rather highest in the average lattice parameter. So what essentially we have on the scale is the least lattice parameter on the left extreme and the highest lattice parameter assuming the portion in the right extreme, and on the average it lies in between. So there is a continuous increase in the lattice parameter on the scale, and the average lies in between. Now when you consider the population distribution of the alloy, when you place the when you position the alloys in such a way that or based on their magnitude of the lattice parameter, and the population of the alloy is rather concentrated on the average of the lattice parameter, what we essentially end up having is we end up having some sort of a normal distribution. So what essentially we have done is we have considered the lattice parameter of the n alloys that we have developed, and based on the magnitude of the lattice parameter we have been placing these alloys on a scale. Now when the population of these alloys, when we place it based on the magnitude of the lattice parameter, is concentrated or relatively more concentrated on the center, that is the average of the lattice parameter, and as we move away from the average, when the population gets gradually decreased, what we end up having is a normal distribution. So what essentially the way we arrived at this normal distribution is, once we have placed all the n alloys onto the scale, we have created certain bins, and these bins, they have a specific range of lattice parameters. So each of these bins there is a specific range of lattice parameters, and now when the lattice parameter of a given alloy falls within range, we categorize into that bin, we place it onto that bin. So instead of rather continually placing these alloys on specific points, exactly on the specific points on the scale, we are creating a bin that includes the range of lattice parameter, and now whenever an alloy falls within this range, we are placing that alloy onto the bin. And this, when we are placing on all the alloys that fall on a given bin, we are rather stacking it one over the other, and that ultimately leads to what we refer to as the histogram. So on a scale, we have the distribution of n alloys based on the magnitude of its lattice parameters. Now we are introducing a bin which is nothing but the range of lattice parameters, and within this bin which is nothing but the range of lattice parameter, all the alloys that assumes the lattice parameters of this range will be placed. And now instead of just collecting these alloys within a bin, we are stacking it one over the other. That gives us histogram, and the histogram will be of this form here. So this will be the histogram. Now we are rather fitting a curve over this histogram, and this is what we refer to as the distribution curve. N alloys on a scale, introducing a bin translates to histogram, and when we fit a curve, we end up having a distribution curve. Now, as we have considered, it is possible in most cases what we observe is the population of the alloys is rather highest in the average of the lattice parameters. Most of the alloys, they rather assume the average lattice parameter, and when you move away from this average lattice parameter, the population gradually decreases, and that is what we refer to as the normal distribution. Now it is also possible that in some materials, perhaps it is also possible that a major portion of the alloys would assume a value that is in the lowest range. It is also possible that in some combination of elements, it is also possible that the N alloys, the major portion of the N alloys, they might assume, or they might gather up, they might rather be concentrated on or they might assume a value that is in the least of the lattice parameter. So, and when you move away from the least of the lattice parameter, the population, the number of alloys assuming that particular lattice parameter will gradually decrease. So what essentially we have is, apart from the normal distribution, it is also possible for us to have n different alloys, and the population of this a major portion of this n different alloys might assume the least of the lattice parameter, and we increase the lattice parameter, the population gradually decreases, and such type of a distribution will be referred to as, or it is referred to as, the exponential distribution. And the way again we have arrived at this exponential distribution is again through the histogram. So the histogram indicates that for a given combination of alloys, for a given n different alloys, the least or the lowest lattice parameter is the most populated region, and when you increase the lattice parameter, the population gradually decreases, and this we have arrived from again building up the histogram. And when we fit a curve, and the curve that is offered is what we refer to as the exponential distribution. Now we have considered two cases. One is the population is rather concentrated at the center, or the average lattice parameter, and as we move away from the average lattice parameter, the population gradually decreases. This we refer to as the normal distribution. We have considered another case where the portion of, or the larger portion of the population is concentrated at the lowest lattice parameter, and when you gradually increase the lattice parameter, the population gradually decreases, and that is what is being shown by the histogram. And that when you fit a curve over that histogram, we end up having an exponential distribution curve. Now there are two extremes, one is the lowest and the other is the average. So we assumed in the normal average as the most population, and in the exponential case the lowest lattice parameter assumes the highest population. Now it is possible that somewhere in the middle, somewhere between the average and the least lattice parameter, the population could be concentrated. Again, depending on the system that we are considering, it is also possible to have a system wherein the lattice parameter is concentrated, or the population is concentrated on a specific lattice parameter. And as you move away from that specific parameter, so this specific parameter is not average or not the least one, it is somewhere in between. So it can be any value on the scale, and the population in this any value on the scale is highest, and as you move away from it, as you digress away from it, the population gradually decreases, and when you fit a curve over such a distribution of population, what you end up having is a gamma distribution. So what essentially we have is, we have three different distributions. And all these three different distributions we have arrived at by considering an histogram, and what essentially the histogram tells us is what is the population of alloys that occupy or that assume this particular range of, a specific range of lattice parameters. And if the population, if it is rather concentrated on the average of the lattice parameter, and when it is gradually decreases as we move away from the average, we refer to that as the normal distribution. On the other hand, if the population is concentrated on the least of the lattice parameter, and when you move away from the least, the population gradually decreases, we have exponential distribution. And the Gaussian is, or rather the gamma distribution is, the population is concentrated on a specific lattice parameter, and when you move away from that specific lattice parameter, it gradually decreases, and this is what we refer to as the gamma distribution. And all this we are able to build from the histogram representation, which histogram representation is just stacking up the different alloys that assume the lattice parameter within a given range. Now, supposing if you want to calculate what is the probability of, let us assume one of these cases, let us assume a gamma distribution, and you want to estimate what is the probability of our lattice parameter assuming, or our alloy assuming the lattice parameter of this. So when you want to calculate what could be, or what is the probability of the newly developed alloy that we have built, assuming a lattice parameter of this range that is highlighted in red. So for that case, what essentially we need to do is we need to calculate the area under this curve. So when you want to calculate the area under this curve, rather an elegant way of doing it, or rather a straightforward way of doing it, requires a function that is able to describe this curve here. So far, the distribution as it is, we were able to come up with a distribution directly from the histogram, and what essentially histogram comprises of it is just one independent variable. Now, when we want to make the best use of the output that comes from the histogram, so histogram, it just comprises of one independent variable, and that histogram is what has been translated into distribution curves. Now when you want to make the best use of the distribution curve, then we have to come up with a function that will enable us to calculate the area under the curve. So we must come up with a function that will enable us, just an example, that will enable us to calculate the probabilities or the area under this curve, which ultimately will translate to probability. So only when you have such a function, you will be able to rather estimate the probability of the newly developed alloy or any quantity assuming a given value. So in this case, newly developed alloy and the lattice parameter we have consumed. So we have assumed that however it can be rather extended to any quantity. So you have such a distribution and you want to know the probability of a quantity assuming a specific value. This is possible when we are able to find the area under the curve. So let us try to arrive at an expression. Let us try to arrive at an expression for this distribution. Now in order to do so, it is possible for us to estimate the probability from the histogram. Now when you want to calculate the probability from the distribution curves, we need the function for the curve. However, the probability from the histogram can be estimated by the population for a specific range of bins. So that is the range that is assumed by the bins, and we can calculate the population in a specific bin. Say for instance, if this bin is referred to as small n, so and Pn is the population in that particular small n, and we have say a number of bins, so a number of bins. So therefore, what essentially we have is we have to sum up all the bins, the population of in all the bins. So that is 1 ranging to, so we have a number of bins, so we have to sum up the population in all the bins. So Pi is the population in a given bin, and it ranges from 1 to a. So we are summing it all up. So the entire population we are considering as the denominator, and on the numerator we are considering the bin of our interest. The probability of the lattice, the alloy assuming a lattice parameter within the bin is rather estimated by this ratio here, wherein we are calculating or we are considering the population in that bin of interest, that's the numerator, and in the denominator we are considering the entire population. So the entire population is given by this expression here. Again, this probability calculation is based on the histogram. So we consider all the entire population in the denominator, and in the numerator we are considering the population in that specific bin that we are interested in. Now when we do that, we will be able to estimate the probability of the newly developed alloy assuming a lattice parameter within that desired range. Now For each of this bin, then correspondingly we will be able to measure the probabilities. So what essentially we can do is, for each of this bin, we can measure the probabilities again from the histogram. So we have from the histogram constructed the or fitted a curve, and this curve what we refer to as the distribution, and this distribution again is not associated, it does not have any function to it, it's just a distribution curves. Now what essentially we are doing is, we are now considering, since it is again based on the histogram, we are considering the separate bins and we are calculating the probability of the newly developed lattice parameter to assume the values within each of these bins. So when we do that, what we end up having is, we have a probability curve. Okay, so what essentially we are doing is, in this case it's just a population. In this case, each of these bars in the histogram, they represent the population, and now from the population we are calculating the probability. And then what essentially we have done is, now each of these bars here, now they represent probability. So when you have a distribution curve that comes from histogram, each of these bars, each of these bins, they indicate a population, just a number of alloys, assuming a lattice parameter within a given range. So that is what each of these bars indicates, and that is what we mean by population. Now we are translating this population to probability, and how we are doing it? We are using this expression to translate the population in each of these bins, in each of these bars, to probability. And now when you translate it to probability, we have found out a function that can be rather introduced in the y-axis. Now this curve that you have is no longer a distribution, but it's a function that indicates how the probability varies when you consider different lattice parameters. So when the lattice parameter varies, how the probability of the newly developed alloy, assuming a specific lattice parameter, will vary. So that is what is being captured by this curve here. So here it just indicates the population, so it's just one independent variable. Now we have introduced a function, and this function here, what it talks about it, describes it, how a probability of a newly developed alloy, assuming a lattice parameter, would vary along with the. So when you consider a newly developed alloy, and when you want to know what would be the newly developed, or the probability of this newly developed alloy assuming a lattice parameter or a given lattice parameter, that can be estimated from this curve here. So what essentially we have done is, we have from the population we have estimated the probability, and that probability is what we have considered in the y-axis here. So we have introduced a function along the y-axis, and now it is no longer just a single independent variable system. We have an independent variable along the x-axis and a dependent variable along the y-axis. The dependent variable along the y-axis, it talks about the probability of an alloy assuming a specific lattice parameter. So you have a system and it has to assume a specific quantity, and the probability of that system assuming a specific quantity is what is given by the dependent variable on the y-axis, and in the x-axis you have that independent quantity. So this quantity in our case is lattice parameter. So a newly developed system assuming a specific lattice parameter can be estimated from this dependent function, that is p of x, which is introduced. And the way we have translated from the histogram to this is by considering or translating each of these bars from population to probability. Now if you look closely, what we essentially observe is, when you translate the population to probability, so this translation here we were able to make the population to probability. Again, this translation again, because we have considered histogram, and the histogram allows us to calculate the probability by considering the number of population in a given bin and the total population. So only through this we were able to arrive at this curve here. And what essentially we observe is, the trend in, when you compare a given distribution, the trend in both the distribution and the corresponding function is the same. So supposing if you consider the gamma distribution, so the gamma distribution, it comprises of how the population in a given gamma distribution is rather distributed. So for in this case, in the case of gamma distribution, how the population is spread out is what is given by the gamma distribution. How the population of the allies are spread out is what is given by the gamma distribution. Now we have translated it to a probability function. We have translated each of these bars into probability. So no longer these bars indicate populations, but they now indicate probabilities. And when we do that, the trend, it remains, so the trend remains unaltered. So whatever trend we observed in case of the histogram, in case of the distribution curve, the same trend is also observed when we translate it to a function. So the function and the distribution curve, they exhibit same trend. So in the case of gamma, the distribution curve assumed a definite function. When we translated each of these bars to probabilities and fitted a function to it, the function also exhibits the same trend. Of course, quantitative values would vary, but the trend remains the same. The same is visible in case of the exponential curves as well. So here again, we are considering population. Here we are considering the probability. So the y, in this case, each of these bars, they indicate population, and here each of these bars, they indicate probability. Despite the change, despite the introduction of the function in this case, the trend still remains the same. And the same we can observe in the normal distribution. Even though we are changing from population to probability, the trend, it still remains the same. The translation, during this translation, the overall trend has not in any way altered. So what essentially then we have is, we have now created a function for the different distributions. We have created a function for gamma distribution, we have created a function for exponential distribution, and we have created a function for normal distribution by replacing the population with the probability. And again, the whole reason we are doing this is because we want to calculate the probability based on the curves. And for that, we were able to calculate the probabilities based on histogram. So only because we were able to start from the histogram, start measuring the probabilities from the histogram, we were able to arrive at such translations. And now we have translated, or we have now we are in a position to be able to build a function for each of these distributions. So when we are talking in terms of just distributions alone, we are talking only based on a single independent variable. Now, by considering the single independent variable and by considering the probability of a new system, assuming each of these single independent variable, we were able to arrive at a function, and this function essentially talks about the probability of a new system assuming a specific quantity. And this function is what we refer to as the probability density function. So probability density function, the way we have arrived at the probability density function is probability density function PDF. The way we have arrived at is, we have translated the histogram that represented population, and this histogram was initially translated to a distribution curve, and this distribution curve, which considered again the population, was translated to the PDF. This distribution curve was translated to PDF by introducing or by calculating the probability again from the histogram. So when you are able to replace the population with that of the probability, the function that you end up having is what we refer to as the probability density function. Now the key aspect that we need to understand here is, even though we replace the population with that of probability, now that we have a function, one, it is possible for us to get rid of the histogram, but the trend, it still remains the same. The trend that was originally presented by the histogram still remains the same. Now once you have arrived at this function, it is possible for, of course, to get rid of the function and completely get rid of the histogram and exclusively work on the function alone. But nevertheless, the trend, this is possible because, and there is an equivalency between those two, because the trend that we observe in the histogram is completely reflected in the probability density curve. So therefore, even though we can get rid of the histogram and work exclusively on this, the quantitative aspect, whatever we want to measure is not totally unchanged from the system that we are considering. If the system gives you a normal distribution, and from the normal distribution you have translated and you have moved on to the corresponding probability density function, you will not lose the key factor. And since now that you are working on a function, there are certain advantages to working on a function when compared to the histogram. One of the key advantages is you don't have to no longer stick with the range of the bits. So you are not restricted by the range of bits. You are not restricted, or whenever you want to find or whenever you want to measure the probability of lattice parameter assuming a specific value, you are not restricted by the values of the bins. You can consider any value when you start working with on the functions. So that is one key advantage, and that advantage is possible only when we are able to translate the distribution curves to the distribution functions. And this translation is possible when we are able to estimate the probability and replace the probability or replace the population with the probabilities, and that will ultimately lead us to the probability density functions. So the probability density functions are rather a representation that we gain for histogram, wherein the population is replaced by probability, and then the function that it offers, this probability function that we get, is what we refer to as the probability density function. So since it is again gathered from the histogram, we do not lose rather the trend associated that we once observed in the histogram. Now let us get into the specific distributions, and now we can refer to it as the distribution functions, and let us rather try to express each of these functions. Now we will begin with this rather distribution here, or this function here. By now you will be familiar, and this is nothing but the bell curve, or what we refer to as the normal distribution. And when you consider the normal distribution, the characteristic features that define a normal distribution are rather the mean and the variance. So what we essentially have is a symmetrical curve, and this symmetrical curve we refer to as the normal distribution. And now what essentially we have done to the normal distribution is, now we have replaced the population with probability, and now we have a specific function for the normal distribution, and this function is what we refer to as the probability density function. So what we essentially have is a PDF, a function for normal distribution. Now that a normal distribution we have seen is rather described by mean and a variance, and the trend it carries over when you translate the population to the probability. So therefore the function, the probability density function that we are interested in, will also be dependent on the mean and the variance. So this mean and the variance are rather the features that define the, or that rather provided us with the configuration of the normal distribution curve. So when we are considering the distribution based on the histogram, we were able to describe it based on the mean and the variance. Now that the trend remains the same, even when we translate or replace the population with probability, even though we are discussing in terms of the function, since the trend remains the same, whatever function now we are going to develop for this normal distribution will also have the mean and the variance associated with it. So therefore the corresponding the nature of the distribution curve, the nature of the normal distribution curve that we get from the histogram, since it is being characterized by the two key parameters, that is mean and the variance, and even when we translate it to a function by replacing the population with the probability, since the trend gets carried over, the same parameters need to be introduced in this function as well. The same parameter needs to govern the particular function as well. So therefore the probability density function, that is the small p of x, is, even though the independent variable for this function is x, it is rather governed by mu and sigma, where mu is the mean, and essentially sigma square is the variance, and sigma is the standard deviation. So this is something that we have looked into in the previous lecture. Sigma square is the variance and the sigma is the standard deviation. So essentially what we have is sigma. So these two parameters, they describe the trend of the normal distribution, and same trend is observed in the function as well. So therefore the probability distribution function of the normal distribution is expressed in this manner. The independent variables is expressed in the left side of the semicolon, and the parameters that govern the function are expressed on the right side of the semicolon. And this expression here, the probability density function of the normal distribution, which is based on the independent variable x, and it is governed by the parameters mu, that is mean, and the variance or standard deviation is of this form here. 1 by sigma root of 2 pi and exponential minus mu square by 2 sigma square. So this is rather the expression for the curve that we observe, the function that we observe for the normal distribution. So when you replace the normal distribution or the population of the normal distribution with the probability, you end up with a function, and this is the expression for the function when we are discussing in terms of the normal distribution. So what essentially we have is this function, it is dependent on x and it is governed by parameter mu and sigma. So mu is the mean and sigma is the variance, and this is how the function is being expressed. Now this is the generalized function. Often, so this is the generalized function where the mu and the sigma can assume any values. Now, but often what we observe is, so this is the generalized function and it can be used for any distribution, but often what we observe is in most cases, or often what we see when you consider the normal distribution is the normal distribution curve is often centered at 0. The normal distribution curve is centered at 0, and then the corresponding change is rather can be described by the standard deviation or variance of 1. So in most cases what we observe is that the normal distribution, particularly when you are considering the range, when you are considering when the values that you are considering, the parameters that you are considering, in this case the lattice parameters that we are considering, when even in this case it is just a positive value, the lattice parameter only assumes a positive value, but in your case considering a parameter, a quantity that assumes a value in any of the real numbers. For instance, it can assume a value of any of the value from minus infinity to infinity. So minus infinity to plus infinity. So we are considering a quantity that can assume any values from minus infinity to plus infinity, and it is centered at, so when you consider such a quantity, the distribution, the normal distribution of such quantity will be centered at 0 and the standard deviation will be equal to 1. So when I say that the normal distribution of a quantity that can assume both negative values and positive values, and it can assume any values, but it exhibits a random normal distribution rather. So we are considering a quantity q, and this quantity q is exhibiting a normal distribution, and this quantity q can assume any value between minus infinity to plus infinity. So in that case, the curve, the function will be centered at 0. So that means mu will be 0 and the standard deviation will be equal to 1. The standard deviation or the variance. So this is the standard deviation and this is the variance, and they would be equal to 1. So in that case, so that is something called as standard normal distribution. So in the above expression, what we have is a PDF for the normal distribution. This is a PDF for the normal distribution. Now it is possible for us to have a standard normal distribution, and that means this distribution curve is centered at 0 and the standard deviation and the variance of it is equal to 1. When these two conditions are satisfied, we have standard normal distribution. The PDF for the standard normal distribution can be arrived at by substituting these two values here. So it will be 1 by square root of 2 pi exponential of minus x square by 2. So what essentially we have done is, we have now an expression for the normal distribution curve and for a specific case and also for a generalized case. So this is the one at the top is a function that describes the probability distribution for a normal case. So you have a normal distribution, and the PDF for the normal distribution, the function that describes the probability distribution for a normal case, is expressed by this term here, or expressed by this equation here. Now when we have a specific case for it, when you consider such a distribution that is centered at 0, and this is possible when you have a quantity that can assume any value between negative infinity and positive infinity, and it exhibits a normal distribution. So in that case, what we end up having is a standard normal distribution. Again, this condition is important for the standard normal distribution. We have a quantity that can assume any value from minus infinity to plus infinity. Despite the possibility of assuming any value from minus infinity to plus infinity, it exhibits a normal distribution. So in that case, what essentially we have is, and it exhibits rather a normal distribution that sits centered at centered at 0. For such case, in such case, what we essentially have is the normal distribution. The mean is 0, and on top of it, the standard deviation and the variance is equal to 1. So in this case alone, what we end up having is a standard normal distribution, and the PDF of the standard normal distribution is a simplified form of the generalized version. Now, considering that this expression here, it centers all the PDFs to a given, or all the normal distribution to a fixed point. Generally, any PDFs for a given normal distribution is often attempted. So what essentially this expression gives us, what this expression does is, this expression it rather describes the normal distribution that is centered at 0. So when you consider a standard normal distribution, so what essentially we have in case of a standard normal distribution is, we have a 0 here, and the distribution is rather it is of this form. So maybe it will be better if I first do this, and then, so this is how the distribution of the standard normal distribution look like, the curve of the standard normal distribution look like. So this is how it looks like. Now, depending on the quantity that we consider, so this is possible when we assume that the quantity that we have is, it assumes the value, it has the possibility of assuming a value between minus infinity to plus infinity, and it exhibits a normal distribution centered at the 0, so mu is 0, and the deviation and the variance is equal to 1. Now, this is not always the case. It is possible for us, even when you consider a setup like this, when you consider a scale of this form, it is possible for us to have a normal distribution looks like this. One normal distribution, another something like this, and something like this. So it is possible for us to have these three different normal distributions. So all these are normal distribution, and all the function associated with all these three, that is green, blue and red, all these three can be expressed by this equation here. So we have considered three different normal distribution, and the function, the PDF associated with all the three, that is, we have considered in this case 1, 2, 3, three different normal distribution, and the PDF associated with all these three can be expressed in this way. Now, what essentially we have is these normal distribution, their means are different, and also the variance are different. So both the means and variance of all these three are different. Now, the mean, what it essentially indicates for a given normal distribution curve, what it indicates is where the curve is centered. The variance, it indicates how the curve is spread. Now, when you consider the green distribution to that of the red distribution, the spread of the green distribution is much greater than the spread of the red distribution. The spread of the green distribution, the spread of this green distribution here is much, so the spread of this green distribution here is much greater than, or visibly greater than, the spread of the red distribution here. So essentially what it means is that the variance is changing. However, in addition to the variance, the mean is also changing. Now, if it is possible for us to translate the mean from these different means to 0, then what essentially we can do is, it gives us a platform to visually compare these three distribution curves. If we are able to position these means, these different means to 0, if it is possible for us to shift or play around with these different curves in such a way that all these are positioned at 0, we are not changing the variance, we are just changing, or we are operating, or we are working on these different curves in such a way that we are making, or we are shifting them in such a way that they are being positioned at 0, then it becomes possible for us to compare their deviations, to compare their different features. So that possibility of shifting the mean from anywhere else to 0 is what we refer to as the standardization. So what essentially standardization does is, the standardization, it shifts the mean from any place to that of the 0. So it shifts the scale, it plays around with the scale in such a way that the mean is shifted from any position to that of the 0. And in the same way, what essentially we can do is, it's also possible for us to, rather for a given curve, it is possible when you consider a given curve, it is possible for us to change the scale here in such a way that the variance is also similar to that of the standard normal distribution. Let me repeat, we have 3 different curves, and these 3 different curves have different mean and different variance. Now when you consider the standard distribution, what we essentially have is the mean coincides with 0, and in this case the 3 different curves, the mean does not coincide with 0. So what essentially then we can do is, we can work around with the scale in such a way that the scale that we have considered in such a way that the parameter magnitude, the x that is this x, we can work on that in such a way that the mean goes back to 0. We can play around with this x in such a way that we can introduce and we can introduce new, or we can replace or scale this x in such a way that the mean of each of these translate to 0, and for each of these curves, when we appropriately change the x, then for each of these curves we can create 3 different curves which are standard distributions. For each of these curves we can create a variant of the standard distribution. So for instance, if I replace x with z1 and x with z2 and x with z3, so this z1, z2, z3 are the scaled variables, and when I introduced, for let's say for red I'm using z3, and for green I'm using z2, and for blue I'm using z1. So what I'm changing is, I'm changing the variable, I'm scaling the variable, and when it is possible for me to scale the variable in such a way that these different distribution functions are centered at 0, they are centered at 0, and then they exhibit a standard deviation and the variance of equal to 1. So it is possible for me to play around with this variable, to translate, to scale this variable in such a way that I'm able to shift each of these distribution curves and change it to the normal distribution, and that is what is referred to as the standardization. So the way we can arrive at, so way we can translate a given variable x to z in such a way that we translate any given normal distribution to a normal or standard normal distribution is, we consider z x minus mu by sigma. So when you have this expression, when you use this expression, and when you translate the x to z using this expression here, because each of these curves here have a specific sigma and a specific mu. So each of these curves here, they have a specific sigma, a specific mu, and when I translate using the x to z, so this is x here, and when I translate this x to z using the mu and sigma for each of these curves, then what essentially I am doing is, I am translating a normal or a normal distribution, any normal distribution, to that of the standard normal distribution, and that is what we refer to as the standardization. So what essentially we have seen is, we have arrived at, or we have seen what is a PDF of a normal distribution, and this PDF of a normal distribution is rather defined by mean and the variance. So the expression will be of this form. It is defined by mean and the variance, and it is possible for us to translate or replace this variable to z in such a way that the new function that we have developed is, so this is fixed and this is fixed, so mu will be 0 and this will be equal to 1. So ultimately the function is dependent on z alone. So what essentially we have arrived at is, we have now seen a way of translating any standard normal distribution or any distribution, any normal distribution to the standard normal distribution, and this is what we refer to as the standardization. So we have seen a PDF, and this PDF for the normal distribution curve is rather dependent on the mu and sigma. Mu is the mean and the sigma is the standard deviation, and it is possible for us to standardize this expression, that is the expression that is dependent on mu and sigma, to an expression that is rather wherein the mu is 0 and sigma is 1, and that is what we refer to as the standardization. We have looked into, we have translated a distribution to a distribution function. We have seen what a probability distribution function is, and towards the end of this lecture, what we have seen is it is possible for us to convert any normal distribution to that of the standard normal distribution by appropriately changing the variable from, in this case, when we change the variable from x to z, it is possible for us to translate any normal distribution to that of the standard normal distribution. So with this, we would wind this lecture up, and we will consider the similar operations for the other two functions or other two distribution in the subsequent lectures. Goodbye.